Alright guys, we're going to be talking about rational and irrational numbers today. I found this cute little cartoon. He's irrational and he goes on and on. See, it's a little pi guy. So if you would plug pi in your calculator and hit enter, that decimal goes on and on and on. Look at this little psychiatrist divide. I think that's poor taste. So, here's a nice Venn diagram showing you what rational numbers are and how integers are housed in rational numbers, and counting numbers, or natural numbers, 1, 2, 3, 4, 5, is housed in integers. Okay? So pretty much the only thing separating counting numbers from integers is the zero and negative numbers. Okay? So rational numbers are numbers that can be written as a fraction with an integer on top and on the bottom. Here's some good examples. Okay? So when written as a decimal, rational numbers will always have a terminating decimal, like we see here with this 0.4, it stops after the 4, or a repeating non-terminating decimal. Let me show you what that looks like. Let's go to our handy-dandy calculator and pull this back up. So, an example here. Let's see if I can make my calculator a little bigger. Well, I don't know, guys. I think my calculator's not going to get much bigger than this. So, a repeating non-terminating decimal would look like this. Let's take 1 over 3, which is a rational number, hit enter. I'm going to hit my SD button, and see that bar? That bar means it goes on and on forever. Let's look at another example. Let's do 1 over 25. Hit enter. Hit the SD button. Oh, never mind. That was terminating. Let's try, I don't know, something off the wall. 13 over 17. Hit enter. SD. Whoa! But if you look, that bar means there's a repeating pattern going on. Okay, so integers written over integers is the key here. And those are rational numbers. So let's check out some example of rational numbers. Whoopsie daisy. So take your calculator. We're going to go 5 over 10. Hit enter. Hit the SD button. We get 0.5. It's rational. Let's do the next one. 5 over 11. .45, notice that's repeating, so we would have 0.45, 45, 45, on and on. Let's do the 12. There we go, 12. Now we get 0.41, and the 6 is repeating, so that would look like this. 0.41, 6, 6, 6, 6, 6, repeating. And the 13. And again, we get that 384, 615 repeating. So let me write that. 384, 615. And this is repeating, so I'm just going to rewrite it. And it goes on and on. Okay, these are all examples of rational numbers. More example of rational numbers, 3 over 1, that's 3. 3 over 5 is 0.6. 6 over 5, 1.2. Now look, I warned y'all about this example right here. Okay, this root 3. If we were to break this up, we would get 4. Let's see, how many times I go into 4? Alright, 16, 4 and 4, you get 3 pairs of 4s, okay? but that 2 is rational because we get this whole number. Negative 1.3, or negative 1 over 3, you get the negative 0.33, again, repeating. We already saw this example. Negative square root of 4, square root of 4 is 2, so we get a negative 2. Square root of 25 is 5. Again, all rational numbers, okay? Irrational numbers, on the other hand, are numbers that cannot be written as a fraction with an integer on the top and the bottom. Examples are root 2, pi, and root 3. So if you have your calculator, let's just type in root 2 here, and I'll show you what I mean. Hit the SD button. So if you look at the decimals, there's no pattern, and you don't see a line on top, which means it's going to be random forever and ever. Same thing with pi. If you hit shift, the X10 down here, we get the pi symbol. Hit the SD, again, goes on and on randomly. And root 3, just to prove a point, equals SD, again, random decimals. So these are examples of irrational numbers. When written as a decimal, irrational numbers will always have non-repeating decimals. So as we just showed you, root 3 would be this long number. It goes on and on forever. Granted, the calculator is limited, so it's probably rounding this 8 from something. Or probably didn't need to round it at all. And the same thing for this root 2. The calculator is limited, but it goes on and on forever. And again, this 2 could have been rounded up or not at all, because I don't know what that next decimal is. Okay? So, can you figure out why root 4 is a rational number? Well, you should know. Root 4, square root of 4 is 2. 2 is rational. 2 can also be written as 2 over 1, which follows our definition as two integers, top and bottom. Good examples of irrational numbers. Pi, we already talked about it. Root 2, root 6. Notice, essentially, these are numbers left in the house. Okay, remember when we have numbers left over when we're simplifying? Pretty much, if you ever have a number left over under the radical, it's going to be irrational. Okay? Now, here's some good notes you're going to need to jot down. If you have a rational plus a rational number, it's going to be rational. Oops, let me make a better looking R. If you have a rational times a rational, it's going to be rational. Now, if you have a rational plus an irrational, it's going to be irrational. If you have a rational times the irrational, it'll be irrational. And then this guy, he is a little tricky. Rational times irrational will give you irrational, but I have a counterexample to this. So let's look over here. If I have root 2, that's irrational, times, that's what these stars are, they're being multiplied, another irrational number. Let's see what's going on here. Well, you told me in class 2 times 2 is going to be 4. Well, what's the square root of 4? 2. That's going to be irrational. Rational. Jeez, you get a tongue twister. But if you look at it on the other hand, if you get root 2, which again is irrational, times another irrational, like maybe 3, you'll get root 6, and this is irrational. So you really got to be careful with this irrational times irrational. Sometimes it might turn out rational, sometimes it might be irrational. So go ahead and jot these down in your notes, because you're going to need them. I'll pause the video if you need to. Oh, it looks like a smiley face. So, copy each of the following, mark them rational or irrational. Go ahead and pause the video, try it out. Alright, this one should have been irrational. This one's going to be irrational, irrational, rational. This was part of that Venn diagram, that 0. Rational, rational, because square root of 16 is 4. That irrational for that pi, so irrational. And root 5 Can't break that down, so this is irrational. Again, we were right. Let me just make sure. Of course I was. So, have you ever multiplied or added irrational numbers, integers or fractions, and gotten a strange looking answer like pi or I? That never happens. Okay? The product of two irrational numbers will always be rational, and the sum of two rational numbers will always be rational. Good stuff. You'll learn that in advanced algebra. It's for imaginary numbers. Okay, yeah, numbers that don't exist. But what happens when you start multiplying rational numbers with irrationals or adding rational numbers and irrational? Well, you get those irrational numbers. So before we explore that, let's take a look at some other possibilities. What is x times 3? Well, as you know, it's going to be 3x. But that's just a shorthand way of writing x times 3, or 3 and x are not the same kinds of symbols, not like terms. So you can't make one number out of them. So we need to remember what this is saying is, when you have 3x, you're really saying 3 times x, okay? But y'all already know this. This is back from coordinate algebra stuff. What is x plus 3 equal to? Well, unless you have a particular value to plug in for x, the only way you can write this answer is x plus 3. Is x plus 3. You can't combine the x and the 3 because they're not like terms. And again, this was going back from coordinate algebra, just re-emphasizing these properties. Multiplying and adding rational numbers with irrational numbers is the same way. They are not like terms, so you can't combine them and get the exact answer. So anything times an irrational number is going to give you irrational numbers. Obviously, except for that previous example where we took irrational times irrational. Alright, so 2 plus root 2 equals 2 plus root 2. There's no way to write that exact answer as one number or one symbol. Same thing for 2 times root 2 equals 2 root 2. There's no way to write that exact answer as one number or symbol. But this is almost like common sense. Okay, guys? So, are 2 plus root 2 and 2 root 2 rational numbers or irrational numbers? Well, the fact that they got this root 2 tagged on, they're going to be irrational numbers. Okay? So, what is the definition of rational number? Again, a rational number can be written as a fraction with integers on top and the bottom. Is that true for 2 plus root 2 and 2 root 2? The product of a rational number and an irrational number is always irrational, unless the rational number is 0, obviously, because anything times 0 is going to be 0. And again, these guys are going to be irrational. Going back up here, or going right here, the sum, on the other hand, of a rational number and an irrational number will always be irrational. Okay? Essentially, if an irrational number is involved and it's being multiplied or added, it's going to be irrational. Unless we have those cases from, again, like if you had root 2 times root 2, these are two irrational numbers, but you get root 4, well, square root of 4 is 2. Unless you get some strange cases like that, that's the only exception. So, checking for understanding. Go ahead and pause the video again, and I'll take the time to mark if they're rational or irrational. Alright, 2 plus a half, that's going to be rational. Pi plus 11, that's irrational. 3 times root 2, well, that root 2 is irrational, so skadoosh. Square root of 9 is going to be 3. 3 plus 7 is 10. That's a rational number all day long. And point 11 is terminating, which means that's rational. Root 4, well, square root of 4 is 2, so that's rational. Rational plus rational is going to be a rational number. Okay? So, here's some quick practice problems. Go ahead and pause the video again. Try to knock these 5 out real quick, and then hit play. Alright, we're back. 10 plus 0.01 is terminating decimal. Guess what? Rational. 12 plus 0.05, rational. 15 plus 0.07, rational. Again, these are terminating decimals. I can write these as fractions. An easy fraction to think of is 1 over 100. 5 over 100, which could be reduced. 7 over 100. This would be 2 over 100. Again, rational. Root 7, on the other hand, is irrational, so this guy's going to be irrational. So pause the video again, try 6 through 10. Alright, we're back. So root 11, that's irrational, which makes the whole thing irrational. Root 17, again, irrational. Root 20, remember when y'all broke this up, you get 2, 10, 2, and 5. The 2's are going to move out, but this 5 stays there, which makes it root 5. So 2 root 5. The fact that you still have that makes it irrational, which makes the whole thing irrational. 225, well, that's 15. This is 25. Those are two rational numbers, so it makes the whole thing rational. Square root of 36 is 6. Square root of 64 is 8. Two rational numbers means it makes it rational. I'm telling you, I'll bite my tongue 5 or 6 times doing these slides. And that's it. Go ahead and knock out that quiz is and see if you get 100 on it. All right. See y'all later.